Chapter 3. The Deep Learning Revolution. It didn't feel like a revolution at first. There were no protests in the streets, no declarations of independence, no overthrow of old regimes. Just a quiet hum in server rooms, a flicker of code on screens, a slow, steady climb in accuracy charts. But what happened between 2006 and 2016 was, without exaggeration, one of the most profound technological shifts in human history. It was the moment machines stopped being told what to do and started figuring it out for themselves. This was the deep learning revolution, and it changed everything. Before deep learning, artificial intelligence was brittle. It worked only when the world behaved. Give it clean data, clear rules, predictable patterns, and it could perform miracles. But show it a blurry photo, a misspelled word, a sentence with sarcasm, and it collapsed. It had no intuition, no common sense, no ability to generalize. It was like a brilliant student who could solve textbook problems but froze when asked a question not on the syllabus. Deep learning changed that. It didn't try to program intelligence. It tried to grow it, layer by layer, neuron by neuron, through exposure, through repetition, through failure and correction. Like a child learning to walk not by reading instructions, but by falling down, getting up, adjusting balance, trying again. The breakthrough came from revisiting an old idea, neural networks. Not the shallow ones of the 1950s or 1980s, but deep ones, networks with many hidden layers between input and output. Each layer learned to detect increasingly abstract features. In an image, the first layer might detect edges. The next, shapes, then textures, then parts of objects, eyes, wheels, leaves, then whole objects, faces, cars, trees, then scenes, a beach, a kitchen, a street. The deeper the network, the more complex the understanding. But training such networks was nearly impossible until Geoffrey Hinton and his students cracked it. They used a technique called unsupervised pre-training followed by supervised fine-tuning. In plain terms, they let the network learn basic patterns from unlabeled data first, like letting a child wander through a museum before giving them a quiz. Then they fine-tuned it with labeled examples. This is a cat. This is not a cat. The combination worked. The networks got deeper. The results got better. Then came AlexNet in 2012, a convolutional neural network designed by Alex Krzyzewski, Ilya Sutskever, and Geoffrey Hinton. It entered the ImageNet Large-Scale Visual Recognition Challenge, a global competition where teams tried to classify 1.2 million images into 1,000 categories. Previous winners used traditional computer vision techniques, handcrafted features, complex pipelines. AlexNet used raw pixels and deep learning. It cut the error rate nearly in half, from 26% to 15%. The second-place team didn't even come close. The AI world gasped. Some refused to believe it. Others scrambled to replicate it. Within a year, every top team in the competition was using deep learning. Within 2 years, error rates dropped below 5%, better than human performance. Machines could now look at a photo and say, with near certainty, "This is a golden retriever playing in snow," not because someone programmed the definition of golden retriever, but because they had seen thousands of them and learned the pattern. This was the turning point. Deep learning wasn't just good at one thing. It was good at everything if you gave it enough data and enough layers. Speech recognition improved overnight. Before deep learning, voice assistants misunderstood half your words. After, they got 95% right. Siri, Google Voice, Alexa, all rebuilt on deep neural networks. Suddenly, talking to your phone felt natural, not perfect, but close enough. Machine translation leaped forward. Google Translate had been clunky, literal, often nonsensical. In 2016, Google switched to a neural machine translation system. Overnight, translations became smoother, more contextual, more human. It didn't just swap words, it understood phrases. It preserved meaning. It even handled idioms sometimes. Then came generation. Not just recognition, not just classification, creation, machines that could write, that could paint, that could compose. In 2015, Google released Deep Dream, a program that visualized what neural networks saw in images. Feed it a photo, and it would enhance patterns it recognized, turning clouds into eyes, leaves into dogs, buildings into temples. The results were hallucinatory, surreal, beautiful. People called it AI art. It wasn't not really. It was a visualization tool, but it hinted at something deeper, that these networks had internal representations, that they imagined things, that they could remix reality. Then came WaveNet from DeepMind, a system that generated human-like speech, not robotic, not stitched together from recordings, but synthesized from scratch with breaths, pauses, inflections, emotion. It sounded so real, listeners couldn't tell it wasn't human. Then came GAN's generative adversarial networks, invented by Ian Goodfellow in 2014. Two networks. One creates, one judges, they compete. The generator tries to fool the discriminator. The discriminator tries not to be fooled. Over time, both get better. The result? Fake faces that don't exist. Fake videos of people saying things they never said. Fake paintings in the style of Van Gogh. The line between real and artificial began to blur. And then Transformers. In 2017, a team at Google published a paper called "Attention is All You Need." It introduced a new architecture not based on recurrence or convolution, but on attention. The idea was simple. When processing a sentence, don't just read word by word. Look at all the words at once. See which ones matter most to each other. Let the machine decide what to focus on. It was a leap. Transformers trained faster, scaled better, handled longer sequences, and they were astonishingly good at language. In 2018, OpenAI released GPT Generative Pre-trained Transformer. It was trained on billions of web pages. It learned grammar, facts, style, tone. Ask it a question and it answered. Give it a prompt and it wrote a story. It wasn't intelligent, not in the human sense, but it was coherent, creative, sometimes insightful, sometimes eerie. GPT-2 in 2019 was so good at generating fake news, OpenAI initially refused to release it, fearing misuse. GPT-3 in 2020 had 175 billion parameters. It could write code, compose poetry, mimic famous authors, answer exam questions, even pretend to be a therapist. People began to wonder, is this a tool or something more? By 2021, deep learning was no longer a subfield of AI. It was AI. Every major tech company had a deep learning team. Every startup claimed to use it. Every product, from refrigerators to insurance apps, boasted AI-powered features. Most of them were shallow, some were scams, but the real ones, the ones built on deep neural networks, were changing the world. Doctors used it to detect tumors in X-rays faster than radiologists. Farmers used it to monitor crops from satellite images. Banks used it to detect fraud in milliseconds. Writers used it to brainstorm ideas. Designers used it to generate logos. Musicians used it to compose melodies. But it wasn't magic. It had flaws. It needed massive amounts of data, often scraped without consent. It reflected the biases in that data, producing racist, sexist, toxic outputs. It was a black box. No one could fully explain why it made certain decisions. It hallucinated, inventing facts, citing fake sources, confidently statting nonsense. And it cost a fortune to train, locking innovation behind corporate walls. Still, the revolution rolled on. Because for all its flaws, deep learning worked. It delivered results. It solved problems people thought were decades away. It made machines that didn't just compute, but perceived, predicted, created. And it was only the beginning. Because deep learning didn't just change what machines could do. It changed how we thought about intelligence. We used to believe intelligence required logic, rules, symbols. Deep learning showed us that intelligence could emerge from pattern, from statistics, from noise. That you didn't need to understand something to replicate it. That behavior could be decoupled from comprehension. That was unsettling and thrilling. The deep learning revolution didn't come with banners or speeches. It came in silent updates, in App Store releases, in research papers read by thousands. But its impact, that was deafening. It reshaped industries, redefined jobs, rewrote the rules of creativity, and forced us to ask, if a machine can write a sonnet, paint a portrait, diagnose a disease, what exactly is left for us? The answer, as we would soon discover, was not simple. But the question, that was just getting started.